Okay, welcome everybody to FinTail Gladiator Prototype AI by our own John McGrath. I'm going to go ahead and hand it right off to you, John. But for anybody watching this recording, this is a student-run lecture by John here on Prototype AI.
Hello there, I am John Peter McGrath, here to present a fundamental game programming concept that's necessarily unique to video games: artificial intelligence. It has come since the days of Space Age and Pong, and we cover a lot of ground in AI, both in general computer science and video games. However, we are not going to focus on sophisticated theory-level AI, as we aren't close to utilizing quantum computing. However, we will go through the steps showing how easy it is to make game AI. Programmers can create artificial intelligence in any manner as desired. They can often fill specific roles depending on purpose and objectives. AI requires controlled behaviors to operate any scenarios. As for video games, AI can be used to reflect any player behavior and progress. AI can be used for allies, or they can be suited as opponents. Video games often encourage competition, which is why making AI opponents is naturally appealing to most game development. However, there are exceptions that game AI is used that isn't player versus AI competition. Game AI, when used to tie in the game core loop, can be a massive replay enhancer because programmers can do anything with them. The AI can range in from various scopes and niches. At the most basic level, AI can be made to simply move independently without player control. However, AI can easily be programmed to do more, such as doing something unique that the player cannot do or mimic player movement to some degree. More elaborate AI techniques include, but are not limited to, state machines, behavior trees, etc. Next, we will showcase a game that uses AI in a simple and effective manner, which stems from arcade video games. The game is Joust, an arcade video game produced by Williams in 1982. One or two bird riding knights simultaneously survive inside the world of rock clouds and hot lava by defeating various buzzard vulture riders. All riders have lances, and the one who collides higher than the opponent by lance wins, knocking the lower opponent off their bird. Players and opponents operate under the same rules, but we'll focus on the opponents. I researched this stuff from Joust Master, a website dedicated to the video game Joust and its sequel, Joust 2. When looking at the makers behind the game, I found out how the behavior of the opponent riders work, which represent a progressive difficulty from wave completions. The red rider is the bounder, the first opponents for early waves. They often move straight and flap erratically, making easy practice targets. They try to hit the player at horizontal level. The next opponent is the white rider is called the hunter. They are more clever than bounders since they respond to player behavior. Their victory method is to carefully position themselves to get above the player with timing. They will stop and turn to reach player from below, but will fly when they miss or are close. They try to defeat the player vertically. And finally, the blue opponent rider is called the Shadow Lord. They prefer to rush towards instant victory by hitting the nearest player, whether running on the ground and then flap quickly, or they fly flat faster than the player when the player is in the air to hit unsuspecting players. However, their high speeds lead them to hit against edges and terrain, allowing skilled players to read their move and then steal victory. So basically, what you see here is AI behavior working in real time. And that's how And that's how the pathfinding gets updated to, or the AI behavior gets updated in real time so that the AI stays alert. What they both have in common is that they can both flap and move, because it makes sense that both the player and rider share the same set of gameplay rules and basic controls. In theory, that would mean a base class like a bird rider would have been made before making subclasses for player rider and opponent rider, where the player simply controls with the player input while the opponent is controlled by AI logic. In this class diagram, you would see that the base character controller / entity is the one responsible for registering all actions. And then, as a big thick arrow splits, then the player character controller inherits from the base, with the controller input being a component. On the other side, you have the opponent character controller, where its AI logic gets inputted into the opponent controller. So that's why you see signs of inheritance being a key part in game development. Can you tell me any examples on what games you've played that has the example of a player controller and opponent controller?
The first one that I thought of was probably Bomberman. I would assume it mimics a very similar structure to this. Also, John, am I allowed to ask questions?
Go.
I'm curious. So you have here the base controller or character entity, and then you have the player character controller and the opponent character controller, and then you have input and then AI logic. Just because I'm not sure if I quite understand, what would be the difference in architecture, or the difference in the difference in what they're actually doing between the player controller and the opponent controller? What are those two things doing differently than each other?
Well, basically, that's a great question, because on the left, you see the player character controller deviates from the base character controller. And with the dashed arrows on the bottom, the controller input is injected into the player character controller. Think of it as like the input handler is injected into the player character controller. And on the right side is the opponent character controller. The AI logic, like pathfinding and state machines, are injected into the opponent character controller.
So are the player controller, the player character controller, and the opponent character controller, are they mostly just a translation layer between the controller input up to the base character?
For the most part, yes.
Okay.
That's how things would work. Anybody else have examples of games you played where the player, and the AI play by the same or very similar rules? Outliers are welcome.
You're like Star Fox?
Super Smash Brothers?
Yeah, that's a good one.
StarCraft?
Huh?
StarCraft?
StarCraft.
Oh,
Play a lot of that. I play a lot of that. So it was either that or Killzone. And I was just like, all right, Killzone, not really.
Oh yeah, that's, as you can tell, this is pretty much a very common way to create multiplayer games that involve AI opponents to make single player games enjoyable. And I can tell you that there's some very infamous AI behavior from Street Fighter 2 that the AI opponents deliberately put those moves that are impossible for players to pull off. So that's one of the outlier AIs that don't play exactly the same rules, but each fighter acts as a character controller, which then has the input get injected, whether it's the player or the AI opponent.
Hey, John, I have a question. And this probably goes off of just the basic fundamentals, but how does AI, I guess from a development perspective or just from an AI perspective, how do you how does AI work when you try to increase the difficulty of the AI, or it's kind of like self-learning? So I guess I should not include self-learning because that's a bit complicated. But for example, Super Smash Brothers, you can there's a 1 to 9 scale of difficulty, and the AI gets more difficult with each point. So how is AI developed over that? Because you kind of brought up a great point on how Mortal Kombat, the AI can pull off these great moves that players or myself like can't. So I just want to know how does difficulty work in AI?
Well, developers have to be able to create a series of parameters that will estimate theoretically how the AI responds to different levels of skill play. For a beginner, the beginning level AI would ideally not be very responsive or is not context sensitive, whereas the expert level AI is ideally would make use of the information for anticipating opponent moves, and that extends to any game. Anyways, I'll continue to move on to the next one, since it's going to tie up to how we are going to provide an example on making the opponent work the same as the player. So if anyone decides to take the direction of making the game AI operate the same as the player, then please keep the following in mind. Restrict the game AI to follow the core game loop. Plan what variables and variant classes you want for your AI based on controller template, as in like you can make a character controller, base character controller when it's a fighter, or you want the game to have opponent and player act the same, and then make like derived classes, as I showed the diagram earlier. Do you want playable characters with different moves? That could extend to like subclassing and all that stuff we'll get to later. Make sure that depending on scope, you may only want a few states to many more branching states for more complex controls, because the more complex moves a character makes, the more it necessitates a state machine, which we'll get to it later. Always, for games that opponents control the same player, is that they must utilize the same control action template or derive from character controller for AI logic. For my game prototype, I made an example based on a premise that opponent must play the same as the player. And here it is. FinTail Gladiator. I made it in response from playing Joust aplenty. And what I like about it is that they have easy to understand AI with very simple controls. So I want to focus on a small game that demonstrates the principles of opponent plays the same as player, but with variance. The first step in making the engaging AI is pathfinding, because movement is the most fundamental piece for any game development, whether player control or AI. For my game, I want to achieve the AI movement by utilizing pathfinding, specifically A* across the 2D grid. Need to make pathfinding smooth for opponent, need to acknowledge the use of physics to not mindlessly hit solid objects. Players always move, which requires a path refresher, and with simultaneous players, opponents can choose to seek a random or closest player to then make a plan for attack. Basically, what you see here is pathfinding in a nutshell. It utilizes the flood fill algorithm, which it generally spreads over the path. And as you can see here, it randomly selects the extension direction so that it'll eventually reach to the player target. That takes like a breath first approach, breath first search. It's a standard flood fill, but it is possible to use flood fill alone, but that's not very efficient for more pathfinding AI. With pathfinding, it's necessary to get walkable nodes and neighbors. And it's always guaranteed that there will be obstacles in the way, which means the short path has to be made while avoiding non-walkables. With the fact that the player is always moving, the Pathfinder will refresh to compute a new path with the same rules at a short time interval. With the A-star pathfinding method, there are two costs employed. The G cost of making a new path from the origin, and the H cost represents a theoretical distance from origin to target. The goal is for the actual cost G to come close to the value of H to find the shortest path. And to achieve the cost, you need to check neighbors. In addition to the checking the length, judging the neighbor nodes being walkable also makes the bulk of pathfinding algorithms. If the neighbor is not walkable, then do not include it as path. Checking neighbors usually involve four sides: left, down, right, and up, which are necessary for flood fill and pathfinding algorithms. Some games employ wraparound so AI entities can wrap around the screen to reach nearest target. I put it in there because I want to be a programming genius. I want to have all bases covered as a programmer so I can make AI to suit the game's needs. Oh. And then continuing on with the checking neighboring nodes, sometimes they support diagonal movement. With these nodes consisting of left, down, right, and up, any form of neighbor check and pathfinding is possible. And I always advise you to leave comments and descriptive variables so that anyone can understand. And now we move on to the evolution of pathfinding. Here we see that the opponent fish are moving towards the player, and when player responds or moves quick, opponents will chase towards the player. However, if you noticed on the right side, things aren't always as polished because so the fish are supposed to be moving towards the target, but for some reason they get stuck, zooming endlessly. That's not what I want. And here we're going to test more AI with more fish. And here, when the player gets bumped, of course, with debug features, debugging is always a good idea, especially making the player invincible to test stuff. When the player gets bumped, the pathfinding configuration gets recomputed to guess where the player will be at, and then they'll chase after it.
So then, John, can I ask a question?
Yes.
So I've done less pathfinding than I want to. So this is me being a little bit of a novice in this space. It looks like, so your game is obviously not actually grid based. The movement is not restricted to a grid, but you're still using a grid to represent and calculate A star. Is that a typical way that people handle a non-grid based game?
Partly, and it's also down to the level design. Again, it depends on I use the A star on a grid because it's the easiest way to do it. I am not yet confident to do the navigation meshes as it requires polygons.
Right. Interesting. And then I'm seeing these red boxes around the actual walls. Is that just a dead space that A star doesn't calculate? And is that just to help make sure the fish don't run into the walls?
That's correct.
Cool.
That's
Thanks.
why there's with a grid, it's very advantageous to have a different color to represent non-walkables. And
Awesome.
with this example, the AI actually does tested on how to deal with choking points. As we see it is possible for the AI to navigate through tight spaces. Any other questions before I move forward to the next step?
Nope.
And now, once the pathfinding has been polished enough, get on to the next step, finite state machine, or more generally, state machines. They provide a basis for setting behavior states on AI through any desired conditions. With two or more states, always make sure transition conditions between states are unique, as in they don't conflict, because if you do two states on top to bottom order and they both have the same condition to move to the state, then who wins? The topmost state wins, and the bottommost will never get called. For easy implementation of my game prototype, I went with finite state machine, which controllably restricts the state transition flow and makes behavior management easier for carefully crafted AI. Because if you went with a general state machine that is not finite, then you're going to have to do a whole bunch of endless webs, which is not what you want to do anyways. And so I want to do only a few states so that it'll be easier for me to make a compelling opponent AI. But for your game, you may want to have a finite state machine with branching conditions, like behavior trees and stuff. So I'll show you a few behaviors that I've implemented for my opponent AI. There are 4 of them, and each one has a clearly defined behavior so that the AI will engage with players in distinct ways, and in some part, they emulate various aspects of the player. From the tail provide, the opponent AI has states to behave in some way like the player, such as seek, that seeks players when nothing else happens, fleeing when the player's tail blade is quite close, attacking when very close to the player that's directly facing opponent, and patrolling around the map where they are far away from any nearby player. Some states can be toggled by developer to allow unique kinds of AI, so not all states need to be used. However, when making states easy to toggle, always include conditions that check whether the state is usable or not from that toggle. States can also be used with inheritance so that subclasses can have their own desired behavior from those states. And here
is the quick question. Is that table the order that you would have those states? You were talking about like certain things getting called or not.
Well, it's not necessarily the order, but ordering does matter when it comes to a programming code.
Right.
And having states provide a guideline. What I recommend when you want to do a finite state machine is draw out on a table on a piece of paper or use a visual diagram and point arrows to what states you want the AI to act. Anyways, I'll show some example code of finite state machine. Here, what you will see here is that the first part is the enumeration, which is an easy way to have a list of AI states. And then the next one is the function that checks the AI state conditions, that you check them. What I do is have the state chosen put at false. And then I call the condition of the state conditions and check to see if the condition works. And if it works, then you choose that state. And then the next one in the middle, you'll see the run AI state. And what I did is utilize the switch statement, which is elementary, which is a current state. After you've done the assign the current state, then it does a state behavior based on the case. And finally, there's the AI control input. What I did is to make sure that all the AI's input controls are done before doing the finite state machine, since it's a good idea to let the opponent AI do everything else before making the next decision. Although to the game player, it doesn't really matter too much, but it may matter in programming flow. So what I did, at the maintaining the finite state machine, we run the AI state first and then check the state conditions. After that, it goes to the next frame and it repeats here on after. That's the very fundamental building blocks of the finite state machine.
Can I jump in with another question, John?
Yeah.
So something that I have always had trouble with a finite state run AI is basically the transition point between states and having all kinds of bugs with like it jumping into a state that I don't think it should be into, or it not going into a state when I think it should, or two states fighting for who should be in control. How do you control for that? How do you make sure that it's obvious which state should happen and that multiple states aren't fighting for which state should take over?
First rule, always start small. Test them locally and isolated. Step 2, read every single state condition. When you're doing the programming phase from top to bottom order matters. And make sure that no two state conditions have the same condition. Because if you do, then who wins? Top or bottom state?
Top state.
Top state, correct.
Do I get 10 points?
10 points to Mecha Cleric.
I was just about to say that. Dang it! You guys beat me to the-
Exactly. This is where Mega Cleric like takes over.
Okay, so now after the finite state machine has been implemented, now we get to the fun part, opponent variance. Variance is a broad concept that can involve a range of things, such as simple stuff like tweakable parameters to more complex creations that utilize inheritance for new subclasses with unique behaviors. In Unity, there is the inspector, which you can create different entities, and you can instantly make different entities by tweaking parameters. Parameters can make a big difference with like color palette, speed, movement, attack patterns, etc. Just to name a few. Now for subclassing, it's a very useful tool to have when you want the AI to express something unique that isn't available for a player or the base AI. With subclasses being an easy way to make entities polymorphic, this reminds me of the programming principle that is currently used in software development, including video games. Object-oriented programming. By embracing such terms like inheritance, subclasses, and polymorphism, it can make game production more streamlined when using those concepts carefully. Object-oriented programming should encourage you to not copy-paste code into separate classes, but instead extend from the base entity when wanting to make unique behaviors not available to the base entity class. For my game project, I utilize subclasses to create opponents that behave different from the base class, especially giving them their own variants of some AI states. Combined with variants from variables and organized code, it becomes easier to create distinct opponents, AI for players to strategize, and more. Here are some AI opponents I made for my prototype. Here, you can see with this debugger again, it has waypoints. Waypoints are a very useful tool to examine how the AI acts and whether it satisfies the developer's intent. The green fish moves randomly across the board, which makes it not so threatening to the player. If the player gets close, then it'll simply charge at the player and bump upon collision. It will never turn its tail blade. Therefore, this opponent fish is most beginner friendly. The yellow fish moves somewhat directly towards any present player, but if you pay attention to this diagram and debugger, and when the players squeeze between solids, then it's sometimes possible to avoid getting caught. That is because the yellow opponent's actual target is the edge of the screen based on the angle from XY coordinate distance towards the player. Should the player get close to the yellow tail, it will either attack and partly pause, or it will flee when the player's tail blade is present, right in front of it. The red AI is the patroller. The red fish patrols around the board by creating a waypoint pattern like a circle. It produces a fixed amount of waypoints based on the radius distance between the red opponent and the target player. Players should be careful about these opponents since their movement can look unpredictable. If players get close, the red will attack and then immediately flee before patrolling again. The blue opponent, a very challenging one, is ironically the simplest opponent programmed, as it will always seek the nearest player or attack them within decent range. When the blue opponent is close to any player with speed prediction, it'll do a spin attack while darting across the screen until it slows down, or when the player is too far, which it will seek again. If no player is present, they will wander randomly. To defeat the blue opponent, the player needs to carefully position the tail blade and tease the blue towards the sweet spot. And with that, with all the AI being showcased, it's time to show them in action. And you can
Jump in
see
with
that,
another question there, John.
yeah.
Oh, sorry. Right as you're about to talk. So something that doing state-based AI, at least as far as I've done them, and like I said, I don't have a ton of experience, but it feels to me like there's not a lot of emergent behaviors that come out of state-based AI. And I'm curious if you feel like, your AI can still sort of surprise you, or if that requires a more complex AI system like a machine learning algorithm or something.
Well, they don't have to be always unpredictable, and state-based AI can surprise players. Even the simple ones could surprise players in a moment-to-moment thing, because the player doesn't always do a perfect run. If you watch videos of Pac-Man, the perfect run, that means it's like the game AI is totally predictable, and it definitely plays one way, but for games like Joust and My Game Prototype, it involves random parts, random spawning, random movement. That's to ensure that there will be emergent behavior, primarily from player action. It doesn't have to be all-encompassing emergence like machine-based learning. You don't have to use machine learning or quantum computing to have engaging AI.
Super interesting. I feel like I've learned some stuff already here.
And so, anybody care to watch the video demonstration one more time?
Could
I
you
think I'm good.
describe a little bit of what's... Actually, no, I'll save that.
And here, again, you'll see how the AI does in real time. Yes, there's random spawning. And direction is influenced by player position. So the gameplay will not be the same in a moment-to-moment thing.
I'm just really glad there aren't fish like this actually in the ocean, because then it would make me even more scared to go swimming.
You say something about fish?
I'm glad these kind of fish aren't actually in the ocean. Can you imagine being like swimming and all of a sudden this fish comes and then like throws its tail at you and then like swordfish everywhere, but it's not the nose, it's their tail. They're doing like flips in the water.
Any comments about this demonstration of game AI?
It's interesting. I think like this is game design more so than AI. There's enough going on here that I, as the player, can't identify a lot of what's making the fish, different. Do you have any suggestions as a game designer? What actually, what's going to make two different AIs feel distinct from each other?
Well, it has to be the movement, and it doesn't always have to be apparent from the beginning. Pac-Man with the 4 ghosts. It takes studious play to really distinguish the AI. Think Pac-Man ghosts. They all have the same objective.
That's a great point.
No, this is really good. I like this because I mean, first off, my team, just throwing that out there. But this is really awesome that you're able to actually like I've done A-star like programming before, but in a like database thing. So it's actually really cool to actually see it being used in a game.
That's great, because pathfinding is typically used across video games for navigation and stuff.
Something else that I've had issues with in the past, I'm curious if you have perspective on it, John, is balancing the difficulty, actually, sort of going along with what Jordan mentioned. Like, I feel like it's really easy to make an AI that's really dumb and super easy to overcome. And it's also really easy to make perfect AI. But that gradient in between of like, this is an AI that's going to be very hard, but not impossible, is pretty difficult. Do you have any perspective on how to create AI that, is just hard enough?
Well, you have to do iteration, and please, no mentioning of supporting piracy. If you don't have your own cartridge to dump for your own backup, please don't try to encourage piracy. Anyways, as I was saying, so yes, pathfinding is currently used in video games for navigation. And anyways, it's been very swell talking.
No, thank you. This has been really awesome. I really appreciate it. Again, my team.
Yeah, this is absolutely, John. Oh, Andy dropped and came back in. John, this is absolutely good enough. 10 points for House Rogue. You entertained an audience full of people and taught me a thing or two. This is just to be clear to you, John, this is something that I wanted to come to. Me and David were talking about who was going to administrate this, and I was like, I'll take it easy. Because AI is something that like I said, I feel like I don't know enough about and want to learn more about. Can you give me, do you have any examples of, you're obviously using AI here for pathfinding, and that's the predominantly what the talk is about. I've used it for the same thing in the past, but given that you're talking about state machines, which can be used for so many different things, you even talked about it a little bit. Do you have any examples of AI that you've worked on or know about that don't have to do with pathfinding, but do have to do with state machines?
Oh yeah, state machines is everywhere. Behavior trees can be argued to be part of the state machines. Halo, many first-person shooting games, Halo, Call of Duty, AI, Doom. Well, I don't know about Doom, but there's also state machines being used for visual novels, which are like, theoretically, you can use state machines for anything, whether it be like a transition. You can use it for like going through the passageway. Yes, but in terms of AI usage, state machines are integral. And my game prototype actually does have the finite state machine, as you can see over here. They do different things. And whatever fits to the game design experience, they can be used for anything. State machines and pathfinding are only tools for game developers and designers to make them how they want and always test to make sure it meets the desired goal.
That's awesome, John. I am super intrigued. I'm very I want to write some AI now.
If you want to write AI notes,
Do you have, this is a very practical question, but in Unity, there's like there's the animation state machine. And then there's also like I think there's a specific class that's a state machine, but it looked like your code was a completely custom written state machine. Do you usually write it yourself? Do you use any of those pre-existing tools?
Well, Unity's finite state machine thing has, I think in general, it's like the state machine, as far as I'm aware, is only supported in animation phase because it's really common to use the animation to represent transitions. Therefore, a state machine is used specifically for animation. And for internal behaviors, want to generally write your own custom finite state machine so that it can run in parallel with the animations.
So in this case, you're not doing that, and so you wrote it yourself. But if you were doing something that had to do with the animation, let's say you're Fisher animating in different ways for each of these different states, would you use that animator to control the states, or would you still have a custom state machine that just tells it what animation to play?
Oh yes. Well, basically when you do an animation state machine, you're dealing only with the animation, and you, as a programmer, need to be able to match behaviors based on animation state. So you could theoretically run entirely with animation, built-in animation state machine, animation idle, animation jump and stuff. You could do that, but if you want to have internal parts involved, like the AI behavior, then you're going to want to make your own state machine.
Awesome. This is great. I'm going to come to you next time after Write AI.
Yes, Andy.
Hi, John. Question: before you knew this stuff, what was sort of your path to learning it? Was there a particular book for artificial intelligence that helped you a lot, or some tutorial you followed?
Oh yes, I know a tutorial. I think it's called Sebastian Pathfinding on YouTube. That gave me the basis for actually doing pathfinding AI and the flood fill algorithm by following code one at a time and studying it over again to understand how the internal mechanisms work. And ever since I did this stuff myself and read over it various times, then it allowed me to better utilize other existing assets that use pathfinding, like the Aaron's A*, and that one has pathfinding and grid. And so and they provide the API, so that allowed me to easier understand this stuff.
Thank you. And one more question. Is everything that you taught today, is there a natural, let's say a programmer really likes this topic of AI and really gets into it, is there a topic that comes to you that would be next, that would up the AI game? Is there something in the logical step to learn after what you've taught so far?
I cannot think of immediately, since that part is I felt passionate about. I enjoyed the idea of teaching the fundamentals, but what's the next step is all up to you, how you want to shape the game. Talk to your programming teammates and ask them about it. And by the way, this video should be publicly available after this thing is over so that we can all enjoy it.
I'm going to put this sucker up on YouTube. So not just our current class, you're going to be famous, John, to all of our 50 something subscribers.
Any other questions before we conclude?
Do you have any tutorials that you recommend for A*
Well,
pathfinding or AI?
I think I recommend the Sebastian pathfinding. I recommend the Sebastian pathfinding. Something, you look up tutorials on A* pathfinding Unity with the name Sebastian. It's probably the best one I've encountered, because even though it is 3D, you can easily translate into 2D. And if you take the time to not only type the code and actually test and debug, you can better understand the fundamentals and make your own A* pathfinding and translate your knowledge of A* pathfinding to other pathfinding and grid frameworks. Same thing for any other tutorial you look up on YouTube and you're passionate about it.
Fantastic. All right, John. Well, then let's wrap up for the day. Let's give you a nice round of applause. Thank you, Jonathan. Fantastic. And we will see you again soon. Thank you for being the first person to do a student lecture in cohort 3.
Thank
All
you,
right.
John.
Thank you, John.
Gladly
John.
volunteered.
Yeah, it was fantastic. Very fun. All right. Bye, everybody. Take care now.